All right, starting with number 3, they give us this function, x cubed minus 3x plus 28. If you watched that intro video at all and you were confused, with all of the a sub n's and x to the n's and all that kind of stuff, we're just going to do the same thing now, just with specific examples. Okay, so what we will bring back from the intro video is the rational zero theorem says, okay, now pay attention here, what we're doing here, what the rational zero theorem is doing is helping us find possible zeros. So what we want to do here, the ultimate goal with a problem like this would be to find all of the zeros. Okay, solving for the zeros of a polynomial is something of interest when we are working with polynomials. And in the previous section of 5.5, they would give us a zero, and we would do synthetic division, and boom, we would have it. We would find, a simpler polynomial that we could factor, and that was great. But they don't give us a zero here. They're not going to give us a zero. What we need to do is find the first zero and divide that out, and that will make a simpler problem for us. The thing is, they don't give us a zero. So how do we find a zero? Well, if we don't have anything, we would just start guessing. We would guess, maybe start at 1 and try 2, try 3, try 4. But some of those guesses could be just absolutely pointless because they are not possibilities. All the possibilities look like this from the rational zero theorem. P over Q, where P is a factor of the constant, and Q is a factor of the leading coefficient. Okay? So in this problem, the constant is 28, and the leading coefficient is 1. So all the possible zeros, and this is what we're supposed to do with this problem, is list all the possible zeros. So let's list all the factors of 28. Okay, so 1 times 28. 2 times 19, no, not 19, 14. 2 times 14. How about 3? No, 8 plus 2, that's 10. That's not divisible by 3, if you know the little trick for finding numbers that are divisible by 3. 4, yeah, 4 times 7. No, 5, 6, 7 now. Then 14. Then 28. Okay, so those are all the factors of 28. Except let's think about this. What if I said -1 was a possible factor? You'd say, no, that would come out to be negative if you multiplied it by 28. But what if you multiplied it by -28? Okay, so -1 times -28, that's 28. So -1 and -28 are both possibilities, and so is +1 and +28. And all of these could be either positive or negative. Okay. Now take a look at all these factors. Factors of 28. What number would you say they're over? If you were to write these as a fraction, what would they be over? They'd all be over 1, over 1, over 1, over 1, over 1. Okay, so we have all of these numbers technically over 1. And now we want to, let's see. What I'm saying here is, since all these numbers are over 1, and 1 will always be a factor of any number, we have these over a factor of the leading coefficient already, 1 being a factor of the leading coefficient. Okay, so this is part of our list, and all that would be left after this is to take all of these numbers and put them over any other factors of the leading coefficient. But the leading coefficient only has one factor, that's 1. This is over 1, over 1. All of these are already, by default, over 1, which is the only factor of the leading coefficient in this problem. So we're done. Plus or minus 1, plus or minus 2, 4, 7, 14, 28. Those are all the factors. Now, what we would do with these is these would be all of the possible guesses for a rational number, okay, that could possibly be a zero of this function. So rather than guessing just 1, 2, 3, 4, 5, 6, 7, right, we wouldn't guess 3, we wouldn't guess 5 or 6, because they're not in a list of possible rational zeros. If there's any number that's a fraction that could possibly go into this function and give a 0, it's in this list. It's the only possibility. Let's do number 6. Okay, slightly more involved problem. 2x cubed plus x squared minus x minus 18. We're going to use the rational zero theorem again. To start, let's just list all the factors of negative 18, or of really 18, right? Whatever. We got 1 is a factor, but we'll remember from our conversation up here, it could be a positive or a negative 1. Why? Because I can multiply negative 1 times 18 and I get negative 18, and there you go. Negative 18 is what we're trying to make with these factors. About 2, yeah, 2 goes in there. 3 does as well. 4, no, 4 doesn't go in there. 5, no. 6, yes. 3 and 6 make 18. 2 and 9. And 1 and 18. So those are all the factors of the constant. Okay. And all the factors of the leading coefficient. Let's just make that quick little list here. You got plus or minus 1 and plus or minus 2. So it's all of these are already over 1, so 1 is taken care of. And we don't have to put them over plus or minus 1. You can take my word for it, or you could think about it for a minute. You just wind up making plus or minus 1 again if you divided it by positive and then negative 1. You just get a positive and a negative 1. So we have this much of the list. Now we need to take all of those factors and put them over 2, because it's all the factors of the leading coefficient over all the factors of the constant over all the factors of the leading coefficient. So we not only have this list, we have this list repeated, but over the other factors of the leading coefficient, and the only other factor is 2 in this case. So plus or minus 1/2, plus or minus 2 over 2, plus or minus 6 over 2, plus or minus 9 over 2, plus or minus 18 over 2. Now here's the good news. You think we've just doubled our list. Yeah, there, I missed one there. Let's plus or minus 3 over 2, and plus or minus 6 over 2. What you'll notice here is, say, 2 over 2. What's that? That's a 1. We already had 1, so we don't need to list it a second time. How about 3 over 2? Okay, that's a unique number that's not been listed already. How about 6 over 2? That's just 3. 9 over 2? Okay, that is something that needs to stay. 18 over 2? That's just 9. We already have that, so we get to cross out 3 of those. There's no guarantee as to how many numbers are going to get to cross out in this list, but usually it's at least 1. Okay, so that's how we list all the possible rational zeros. We take all the factors of the constant here and divide it by all the factors of the leading coefficient, just like you see here. Of course, we'll be doing this again in the other problems, such as number 11. F of x equals x to the third minus 12x plus 35x minus 24. Okay, so first, well, ultimately what we're trying to do is find all the zeros of this polynomial. This probably is squared, yes. Find all the zeros, all the numbers that could be put in for x and result in 0. We're not given one like we were in 5.5. That would have been nice, but we're not. So what we'll do is start guessing. But instead of just guessing willy-nilly, just any old numbers, we're going to put the factors of the constant over the factors of the leading coefficient. Okay? So factors of the leading of the constant are plus or minus, let's see, we got plus or minus 1, plus or minus 2, we got 3, 4, not 5, but 6 works, not 7, but 8, not 9, not 10, not 11, but 12, and then all the way to 24. All right. So there's all the possible factors. All the factors of the leading coefficient are 1, just 1. So you divide each of these by 1 and nothing would change. It would still be just the numbers that you see here. Okay, so this here is the list of all the possible rational zeros for this function. So now, the maybe bad news is to test these. Well, first, if we were given a 0, what would we do? We would do what we did in 5.5. We'd put it in here to the synthetic division, and we would get the simpler polynomial and move on from there. The thing about this is we don't have it, so we're still going to do the same process. It's just going to be a guess. We're going to see if it comes out to be 0. So let's try positive 1. Right? We're going to do this over and over until we find a 0 that works. Okay. So bring this down. See, this is 1. 1 times 1 is 1. Negative 11. Negative 11. This is going to be 24. And what do you know? Just our luck. Our first guess worked. Positive 1 is a 0. Okay. That means if you put 1 into here, you'll get a 0. Well, what happened now is, this is the same as dividing by the factor x minus 1, like doing synthetic division, and then getting this simpler polynomial, x squared minus 11 plus 24. And in this, all the zeros of this polynomial are the other two zeros besides 1 for this polynomial, right? Because x minus 1 times this will be this polynomial, so the other two zeros are the two zeros of this quadratic. So if we could factor this, which would be really convenient, x and x, what could we, what two numbers multiply to make positive 24 and negative 11? Well, we know those two negatives. How about 8 and 3? So we set that equal to 0, and we find that x equals 8, or x equals 3. So our zeros are our solution for this problem. The zeros are 1, positive 3, and positive 8. And look right there. There's 3 is a possibility, and 8 is a possibility. 1 was one that we guessed, and it worked out. So there you go. You can see that we were in the original list. The rational zero theorem was correct. Alright, next we are going to do number 16. Okay, just another problem. Now it's a fourth degree polynomial instead of a third, so it's a little bit of an added challenge. It's really just more steps. It's not really any higher level of complexity, just longer. So the first thing we're going to do is make a list of all the possible rational zeros. And you may notice there's just a 1 out here, so that's not going to complicate things at all. We just need the factors of 24. So we have plus or minus 1, we got 2, 3, we just did this, 4, 6, 8, 12, and 24. So we are going to start guessing, just take from this list of not 8 but 16, right, because each of these are positive or negative, so we got 16 guesses here. But that's definitely better than having no idea whatsoever what to guess. Alright, so we begin. Put our 1, negative 2, negative 9, 10, and negative 24. So we'll start guessing with 1. Why not? Put a 1 there. 1 times 1 is 1. Then we subtract and get negative 1. Now we get negative 1. Now we got negative 10. Now we get negative 10, 0, 0, negative 24. So 1 didn't work out. So let's grab our eraser and just get rid of all this stuff and move on to our next guess. Our next guess will be -1. And it might be helpful to cross out that +1. That's never going to work. Okay. So put in -1. So -1 times 1 is -1. Then we get -3. Then we get +3. Then we get -6. +6. 16. And -16. That's not going to work. Okay. So we erase that. Let's try 2. Bring down the 1. We get 2 times 1 is 2. We add, we get 0. 0, -9. 2 times -9 is -18. -8. And we get -16. That's not going to work. So let's get rid of all those. We'll try, let's see, what have we not had work? That didn't work. 2 didn't work. How about -2? 1. -2 times 1 is -2. Then we get -4. Then we get +8, -1, +2, 12, and oh, so close, -24. Be careful here. -24, -24 is -48. So that didn't work. Though if that happens, you might want to just check your work and see if something got a little messed up. But that one was good. That didn't work. Let's try 3. Put 1 here. 3 times 1 is 3. Then you get 1. Then you get 3. Then you get -6. Then you get 18. Then you get, let's see, -18. Then you get -8. And you get -24. Okay, so that was close, but no cigar. That adds up to -48, not 0. So 3 didn't work. Oops. So yeah, 3 didn't work. Now let's try -3. So we get -3, -5, we get +15, we get 6, we get -18, we get -8. Now -3 times -8 is +24, and we get 0 at the end. So we know that -3 is a 0. You need to wind up with a 0 here in order for this to be a 0. That makes sense. Synthetic substitution. That's what this is. This process is synthetic substitution or synthetic division, whichever you like to call it most. And there you go. -3 gave us a 0. And so -3 is a 0. What do we have here? We have the constant term -8. And we have 6x. Then we have -5x squared. Then we have x cubed. All right. Well, so what? What do we do with that? Well, a lot of times we'll do the synthetic division or substitution or whatever. Get this guy. It'll be a quadratic. We'll factor it. It'll be easier. We'll just do it up. But this is a cubed, and this is typically one that we can't just factor. We need to divide, and that's going to be the case here as well. Sometimes you might try, factor by grouping, but that's not going to work. I can see that's not going to work. So we need to do the rational zero theorem again. The good news is we get to make a new list out of this constant and this leading coefficient. It'll be shorter than this one. So we have 1, 2, 4, and 8. Okay, shorter than this list here. The good news is we already know that 1's not going to work, -1. It didn't work up here. It's certainly not going to work in here. If it was a 0 of this guy here, it would be a 0 of this one here. So that's not going to work. Positive, -2, and then 3 is not even part of the list now. So we just have 4 and 8 to try out. So we'll try 4 on this guy here. 1, -5, 6, and -8. Bring down the 1 and go to work. 4 times 1 is 4. And we get -1, -4, 2, and 8. Great. That worked out a lot faster than all these guesses up here. Now we get 0. And we get the knowledge that both -3 and +4 are zeros. And now we're going to take this guy here, which will be x squared minus 1 x plus 2. So x squared minus x plus 2 Can we factor this? Two numbers that multiply to 2 and add to make -1. No, that's not going to work. Okay. So if we can't factor it, what would we do? How do we find those zeros? We use the quadratic formula, and the quadratic formula is x equals -b plus or minus the square root of b squared minus 4ac over 2a. We remember that. So we're going to use the quadratic formula on this guy, but it's going to be really quick to find out. We don't care too much, and I'll show you why. X equals -b, so that's going to be a -1, that's +1, plus or minus the square root of b squared would be 1, minus 4 times a, which is 1, times c, which is 2, over 2 times a, which is 1. Okay, so the reason we don't care is because look what we get inside the square root here. 1 minus 8, that's -7. What kind of a solution is that? It's imaginary. And the instructions ask us to find all real zeros. And this wouldn't be real, this would be imaginary. So there we go, we're all done. We found all the zeros that we care about. Those zeros are -3 and +4. There you go. -3 and +4 are the zeros we were looking for. Just a quick recap, we found them by making a list of all the possible rational zeros using the rational zero theorem, factors of the constant over factors of the leading coefficient, and then tested one of them out, got a simpler one. It was still a third degree, so we did it again. We did the synthetic, found a quadratic, did the quadratic formula to find that we have an imaginary zero, so we just don't even care about those ones. These are the only two that we would report back. Okay. Great. So now let's move on to number 21. And so what they want us to do in 21 is to use the graph of this function to find zeros, to find all the zeros. I can't remind you enough times, I don't think, what a graph is. If we were to put x's in here, put things in for x, put 1 in there and 2, 3, -1, -2, -3, -4, all the possible numbers we could think of. Right? Create like a table of values. We put in all of these x's, and we get all these y's. And then we graph all of these ordered pairs. That's what makes the graph. Right? So at some point I'm going to put something in and get a 0. Right? And we can see that happens here, it happens again here, and it happens again here. I put in something here and for x, and I get a 0 because that's what y is, right here. Y here looks like I think it's like 3 or something like that. Here y is 0 again, here y is 0 again. So at those points, we'll find zeros, or values of x that we can put into the function that make y 0. So let's take a look at this graph and ask ourselves, how many zeros are there? There's 3. There's 3 times that the graph crosses the y-axis. 3 times where an x put into the function makes the function worth 0. So rather than making a whole list of all those rational zeros to start with, maybe we could just look at the graph and find a 0 from there. And it looks like -3 is a 0. Alright, so we'll set up the synthetic division and start with 6, let's see, 25, making sure that if there's any need of a 0 placeholder, we do that, but everything's good. Bring down the 6. -3 times 6 is -18. And now this is 7. When we add these together, -3 times 7 is -21. And this makes -5. And negative 3 times negative 5 is positive 15, and we get a 0. Okay? Remember, if we think of this as, we can think of this in two different ways. Synthetic substitution, synthetic division. Or we could just think about the whole thing as one thing, synthetic division, and talk about the remainder theorem. The remainder is 0, which means that when you put negative 3 into the function, you get 0, which is the definition of a 0, which is what we're looking for. And after this process of synthetic division, we have found the result to be 6x squared plus 7x minus 5. Okay. Now we would like to find the rest of the zeros. And so we could look at possibly this approach for factoring. So we've got 6 times negative 5 is negative 30. I'm going to add a 7. How about 10 and negative 3? 10 times negative 3 is negative 30, and 10 minus 3 is 7, so that works. So we can factor it by grouping. 6x squared minus 3x plus 10x. What's this? Minus 5, right? The last part. We separate the 7x into these two. 10x minus 3x is 7x. But now we can group these together, and we'll get 3x times 2x minus 1. And we'll take out a 5 and get 2x minus 1 out of that group. And now both of these, as should happen, they have a common factor of 2x minus 1. Okay, there's our factored form of this function. We'll set it equal to 0. Right, because we want to know when this function is equal to 0, and something times something equals 0 means that one of those things has to be 0. So we solve for both possibilities. So x could be 1/2, or x could be negative 5/3. So let's just list out our zeros just so we're clear on them. Our first one was negative 3. We found that. Then these two, 1/2 and negative 5/3. Those are our zeros. Okay. Now, after 21, we'll do 24, finding the rational zeros for a slightly more complicated problem. And I guess complicated is too scary a word. It's really just more steps required. Squared minus 8x minus 8. All right. So let's see the factors of the constant. Factors of the constant would be plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. Okay. Any of those is going to go over a factor of the leading coefficient, which we have as plus or minus 1 and plus or minus 2. Okay, so let's make a set of all of our possible rational zeros. That's all of these over 1, and then again all of these over 2. And then if we had another factor of the leading coefficient, we'd do it again, but we don't. So we've got plus or minus 1, 2, 3, not 3, my mistake. I don't see how it could be your mistake. It's my mistake. And now we take all these over 2, got plus or minus 1/2, plus or minus 2/2, plus or minus 4/2, and plus or minus 8/2. Here's something cool. 8/2 is the same as 4, so we can cross that out. 4/2 is the same as 2. You can cross that out. 2/2 is the same as 1, so we can cross that out. The only new zero we got from putting them over 2 is 1/2. So now we've listed all the rational zeros, or possible rational zeros, and we'll use synthetic division to smoke one of them out. Let's try 1. There's just really not a simple way to say this one's a better guess than that one, so we just try it. Pull down the 2. 1 times 2 is 2. Then we get 4. Then we get 4. Then we get negative 4. And then we get negative 4. That's no good. This is giving us a negative 12, and that's not what we want. So let's back up, and we will try now negative 1. We just keep trying until something works. And that worked. So bring down the 2. Negative 1 times 2 is negative 2. We get 0 here. Anything times 0 is 0. Negative 8 plus 0 is negative 8. And then we multiply that negative 8 by negative 1. We get positive 8. And now this is a 0. Okay? So one of our zeros is negative 1. And we'll look for how many more? Possibly 2 more, because the third degree is going to have a maximum of 3 real zeros. Okay, so this is 2x squared plus 0x minus 8. Okay, so we have 2x squared minus 8. Let's factor out a 2. This is 2 times x squared minus 4. This wouldn't take long to factor. If you recognize it as a difference of squares, you can factor it like this. Right? And we'll just set that equal to 0 because we want to find the zeros. So x plus 2 equals 0, or x minus 2 equals 0. So we get x equals negative 2, x equals positive 2. Okay, so we get negative 2 and 2 as the other 2 zeros. Okay, it's just having a number out in front of the, or I guess having a leading coefficient that has more factors, so we have a longer list of possible rational zeros. I'm trying to pick a color. Very important. Okay, number 33. There it is. And so now we'll start making the list of possible rational zeros. So we've got the factors of the constant. That's 1 and 2 for sure. You can see 3 pretty easily. 4 no, 5 yes. 6, not 7, 8. So we've gotten past that. So 3 times 10, of course. And 2 times 15. And 1 times 30. It's a long list. Then we're going to take every one of those over all the factors of the leading coefficient. Okay, so this could be a long list. So we'll start with the originals. Almost didn't fit. Then we'll take each of those and put them over 2. So plus or minus 1/2, plus or minus 2/2, plus or minus 3/2, 5/2, 6/2. We should put commas in here. 10/2, 15/2, and 30/2. And that is our list. Now 30/2 is 15, and we already have 15. We don't need that. 15/2, okay, we'll keep that one. 10/2 is 5. 6/2 is 3. You keep it, yeah, this one's the same as 1. Okay, so now we have a complete list. And we are going to begin. You could make a lot of guesses here, but it's certainly a lot better than having no idea whatsoever. Especially if you didn't have this list, you might try 1, 2, 3, then 4. Well, 4 would be a complete waste of time. You can see here, and 7, 8, and 9. So I know it's a lot of work, but it's not that bad. Okay, so here is something we should recognize as we're writing down the synthetic division. There is no x squared term. Make sure that that's correct. Yeah. No x squared term, so we need to put a 0 there as a placeholder. Then there's 37 and negative 30. And we begin the process. 2, negative 7, negative 7, negative 7. Negative 7. Negative is going to be 44, and that's not going to work. So we'll back up, right, and we will cross out positive 1. That one didn't work. Now let's try negative 1. 2, negative 1 times 2 is negative 2. This gives us negative 11. This is positive 11, negative 11. And this gives us 26, and that gives us negative 26. That's not going to work. So we'll get rid of all that and say negative 1 didn't work. We'll erase that and try 2. 4, negative 5, negative 10, negative 10, negative 20. 37 minus 20 is 17, and that's not going to work. Right, because we want to get a 0 in the end. That would have not done it. So positive 2 is out. Let's try negative 2. So bring down the 2. Negative 2 times 2 is negative 4. Negative 13. Positive 26. 26. Then negative 2 times 26 is negative 52. 37 minus 52. Let's see. So 37 minus 52. Negative 15. And negative 2 times negative 15 is positive 30, and then we get our 0. It's great news. So negative 2 is a 0. So if we were to start a list of zeros, negative 2 would be the first one we found. Okay, and then this, the result here is we got a constant, we got an x term. That's going to be a positive. This is going to be x squared. This is going to be x to the third. So we have 2x squared minus 13x squared plus 26x minus 15. And we want to find zeros of that. And usually, in a lot of these problems, we'll start with the third degree. So we do the first division and wind up with a quadratic. And it's easy to factor that or use the quadratic formula or whatever. But that's not possible here. So we're just going to have to do synthetic division again. So we set up our synthetic division with 2, negative 13, 26, and negative 15. Okay, and we know that positive 1, negative 1, positive 2, none of those work. Something to keep in mind, though, just because negative 2 is a 0 doesn't mean it couldn't be 0 again. Right? That negative 2 could show up multiple times. So that's something to think about. I don't think it's likely, but we might as well try it. We'd hate to skip over it and then find out that that was it the whole time. So let's just try it real quick here. Negative 4, negative 17, positive 34, and that's never going to work. So now we know negative 2 is definitely done. Negative 2 is now done. It's out. Now we'll erase this and start with 3. Get 6, negative 7, negative 21, 5, and 15. We get a 0 there, so 3 is our next 0. I don't like that at all. There we go. And now what we have from this process is 2x squared minus 7x plus 5. Could we factor that? Let's see, we got something other than 1 out here for our leading coefficient, so we're going to use this. 2 times 5 is 10, and then we put a negative 7 here. So could we multiply to positive 10 and add to make negative 7? How about negative 5 and negative 2? Yeah, so now we're running out of room, so let's bring this over here, the next step. Actually, let's bring it a little higher, right there. So we'll have 2x squared minus 2x minus 5x plus 5. Now we group these. We got 2x coming out of here for x minus 1. Let's take out a negative 5. Since this first term is negative, we'll take out a negative 5. And you get x minus 1. Factor out that x minus 1 because they have it in common. And that leaves 2x minus 5. We'll set that equal to 0, which means x minus 1 equals 0, or 2x minus 5 equals 0, and x equals 1, or x equals 5 halves. And we'll see, we must have done that first one wrong. Odd. Just checking the solutions here in the solutions manual. Well, what I'm perplexed about here is we found this 1 here, but at the very beginning of this problem we put 1 in here and tested it with synthetic division, and it didn't work, which means we must have done some math wrong, right? And that doesn't, that makes me uneasy. So I always have to do this again. And this is the last problem, so you can certainly just stop watching this. We did find all the zeros. The other two are 1 and 5 halves, which you'll see are from the original list. 1 and 5 halves are in the original list. Now let's try, no, that's no good. A 1 again, so we put 2 here, and we put 1 times 2 is 2, get negative 7, negative 7, negative 7, negative 7, 30, hello. It would have worked if I had half a brain. That's okay. Those things happen, those, not to excuse my mistake or something, but if you make those mistakes, I make them too, so no worries. We made it through, and we're good to go. We found all 4 zeros. And that is everything. So thank you for watching.